So those of y'all that have done no practice, and I can tell you've done no practice because you don't have any idea what I'm talking about. What we're doing today is going to have to be built off of you being able to do that. What we're doing also. And same thing, you're having a quiz tomorrow over writing 2 Lewis dot structures for a covalent and for an ionic compound. Right, so we said we had 12 electrons to work with. We use 6, have 6 left. So I had carbon, hydrogen, hydrogen, and oxygen. That's where my 6 electrons with. So we have one of those that's attached to the carbon needs some more electrons. So which one would that be? Does the hydrogen need any more? No. So which one? Oxygen. Right now, oxygen only has how many? 2. So it needs 6 more. So when I do that, that uses up all of my electrons. I don't have any left. Is that a good structure? Does everything have an octet? Carbon doesn't, right? Because if I look at my carbon, it's got 2, 4, 6. So the oxygen, one of the lone pairs, is going to actually have to come and form a double bond. So the correct structure would be, and then double bond it, O. It's not an ion. It only has a brackets if it's an ion. All right, if we look at our other one, and I have magnesium. So I said the first step for an ionic compound is to write your element with its valence electrons around it. So how many valence electrons does magnesium have? 2. 2. And how many does iodine have? 7 all that. I couldn't help for a minute there. All right, so that's what I got right now. So we're trying to put those together. So iodine is very reactive because it needs 1 more electron. So that magnesium can donate one of its electron and make this iodine have a full octet. But when I did that, I got magnesium down to just having 1 valence electron, which makes it actually more reactive. So what do I need to add? I got to add another iodine. For this is because in an ionic compound, your positive and negatives need to be equal to each other. So when I did that, then that would tell me that was a good structure. My magnesium lost 2 electrons. And then each of my iodines lost 1 electron. So I have a positive 2 and a negative 2. So if it's an ionic compound, you need to be able to write the formula, which would be MgI2. And then if I name that, it would be magnesium iodide, exactly. I need to put these in brackets. If I notice I have 2 negatives because I needed 2 of those and only 1, so I need to separate them. So I'm going to put one of my iodines over here. It would be a -1. My magnesium in the middle because we have opposites attract, so that the 2 iodines with negative would not line up and be together. And then I need to come back and put the octet around my iodine. And that would be what's actually considered the structure. So for what we're doing today, as far as your answer to your journal, that's what you need to have on that. Anybody have any questions on that? All right. You picked up something else that was an opportunity to get some extra points. This is not a required project. It's just an opportunity to bring up your grade. If you have 100 in my class, you probably don't need to do this because the computer will not take a grade over 100. I would give it to you, but it won't take it. So these points will be added to your third 6 weeks average. So it's due on 12/1 during your class period. So that would be 6. I will not take anything late. I won't take it after school because my mommy or daddy are bringing it. It's due that day during this period. You have to get the element that you are using because it's adopt element. You have to get it okay before you start it. If a student turns in a project with an element that they did not get okay, then they will not receive any credit for that. So whenever y'all did the other projects that were required, then I gave you some partial credit for those types of things. I will not do that for this. These parameters will be followed 100%. So if you flip over of yours, that's the rubric for grading it. Hannah, don't make me ask you to have to take that off. The same thing as having the phone out. I don't appreciate it. This shows you the rubric on this. So see that there's 2 parts. There's an advertisement and then there's also another paper part. Notice that that is an advertisement, not a board with sodium and how many protons, neutrons, and electrons it has. So whenever we did the other project, it was supposed to be an obituary. I had some people that did not turn in obituaries. I still gave them some partial credit. I will not do that this time. So if the student does not turn in both parts of the project, they will receive no credit. If the student does a poor job, then they also will receive no credit. This is worth 60 points if you add everything up. If a student gets 40 points or less, they will get no credit. This is an opportunity that I am giving, hopefully for my students that are failing, a chance to bring up your grade. And so if you just kind of halfway do a project, I'm not giving you credit for halfway doing the project. Right, if you flip over to the other side, a lot of that is just a repeat. It tells you when it's due to be sure and get the element okay through me. And that no exceptions as far as it being late. And at the very bottom, it gives you the scale as far as getting your points. If it's perfect, you'll get 5 points, add it to your third 6 weeks. If you score 59 through 50, you're going to get 4, 49 through 43, and anything lower than that, you will not receive any points for it. Any questions on that? So I put this in Sports U and I sent to the parents that are Sports U that you will be bringing it home. And it's also posted in Google Classroom. So please share it with them also. All right. All right. So let us look at our notes. Oh no, before I do that, but that's okay. Let me flip back. So this is just my reminder. So you'll have a quiz tomorrow over drawing structures. There'll be 2 of each. For the ionic compounds, you also will have to write the formula and the name. You have a test on Thursday over this unit, and it will be an open notes test, which I hate to say because that means some of y'all won't study at all, but if you don't study at all, then you will not get finished with it. Just because it's open notes and you don't know where to go, you're not going to get finished with it. And there will be no exceptions on the time. My Google Classroom tutorial times, last day requiz, all posted in the usual place. There's a video that you can watch tonight that would be helpful for what we are doing tomorrow. I think that is now notes. Right, so we're not there actually, we are. Yes, sir. Go quickly, please, so we can get started. So the table in your notes, I gave that to you filled out. This part, I gave that to you on Friday, filled out, so be sure it becomes part of your notes. Same thing with this chart that y'all picked up today. That needs to become part of your notes. So what I mean by that is when you have your test on Thursday and I say it's open notes, you need to pull everything out that's your notes. You're not going to go back in digging for something else, okay? So if I were you, I would get them and staple them all together. And you know you're going to have them. All righty. So we have what we're doing today, which is called molecular geometry from these notes, and then a little bit about what we're doing tomorrow. So on Wednesday, we'll do a in-class review for the test. Alrighty, so we are going to be talking about molecular geometry. So this is true only for molecules. And if we talk about molecules, we're talking about covalent compounds. So no ionics as far as these structures. We said earlier in the notes that ionics form crystals. Like salt, and that they have a lattice, positives and negatives alternate. Yeah, like a lattice work. So geometry is how elements that are bonded have different shapes, because it's not just all going to be straight or linear. All right. Part of my notes. So molecular geometry is a 3D arrangement of a molecule's atoms. And the molecular geometry can sometimes lead to polarity, which is the uneven distribution of the molecular charge, and that's going to be because of electronegativity differences. And we talked about that under periodic table trends. So the one that comes to mind is water. Oxygen is going to be slightly positive. The hydrogens are going to be slightly, I said that wrong. Oxygen is going to be slightly negative. Hydrogen is slightly positive because oxygen is much more electronegative. So we are going to be looking at something called VSPER, which stands for valence shell electron pair repulsion. Much easier to say VSPER. And that states that repulsion between sets of valence level electrons. So once again, we're really only worried about our valence electrons and surrounding atoms. Or oriented to be as far apart as possible. So electrons are negative. So if they're by other electrons, they're going to try to separate because likes repel and get as far apart as possible. So an example of this is water. So we look at water, and it's covalent. So if I went through my steps, total number of valence electrons. So I would have 2 plus 4. I keep on doing wrong for oxygen. Oxygen is not 4. It is 6. So I have 8 valence electrons to work with. So my oxygen's going to go in the middle. That's always my next step. Put something in the middle and do a single bond to what it needs to be attached to. So in this case, hydrogen. So each bond took 2 electrons. So I used a total of 4. So I have another 4 to work with. Hydrogens only need those 2, but my oxygen has 2, 4, so it needs another 4. So that would be a good structure for water, but it does not reflect what its shape would be. If water, if you think about it, that these are electrons and so are the dots, they are going to be repelling each other. Because negatives or lights will repel. And what we really end up getting is a structure more like this. So this would be linear, just straight across, but water actually has a bent structure. And once again, that's because these lone pair of electrons are repelling the electrons in the bond. So that's kind of what's pushing them down. So that's what we're talking about. We're looking at those, at all of the electrons, and see how they could change the shape. So VSPER in lone electrons, as far as how they affect everything, the lone pair, and remember, lone pairs are going to be what an element keeps. It's not going to be part of the bond. So the lone pair of electrons that occupies the space around the atom, it does so just as bonding pairs do, but the actual shape of the molecule is going to be determined by the position of the atoms only. Lone pairs of electrons repel stronger than the bonded electrons. And that causes the shape to be different. So that's a lot of words that's basically saying the shape of a molecule may not be what you expect it to be. And it's going to be because of these electron-electron repulsions. If you flip to the top of your next page, it talks about hybridization, and we're not worried about that. So you can put an X through that. Complicated looking chart. All right, so to start off with a couple of things that we are not worried about. We are not worried about what's called the electron geometry. We're just going to work with the molecular geometry. And like I said, you don't have to worry about hybridization. So when we're talking about VSPER and its shapes, an A is always going to represent the central atom, because that's really what we're concerned about, what's going on around the central atom. An X is going to be the bonded, and an E would be any lone pair of electrons. So if I go back to oxygen and hydrogen for water, one that everybody's pretty much familiar with. So in this case, my oxygen would be my A because it's in the center. My 2 hydrogens would be my X, or X's, because that's what's bound to the oxygen. And then for my E, which is my lone pair on water, I have 2 lone pairs. So if I put that into a generic formula, which is what we're kind of trying to do, so then you can see what shape it is, it would be A, X2, because it had 1 central with 2 things bonded to it, lone pairs of electrons. And once I got it to that, I could come down here and I could see that it matches up with this one. and then I would come across here and that would tell me that its shape was bent. There are lone pairs around that are on an X, so not on a central atom, but we do not care about those. We are only interested in what is happening around the central atom A. So if you are looking for domains, that's the total number of bonds and electron pair that are around the central atom. And it just kind of gives you a smaller place to try to figure out what it is on the table. So once again, if I looked at water, it has 2 single bonds and it has 2 pairs of electrons. So its domain would be 4. It has 4 things around it. So that would have gotten me to here, and then I would have just needed to choose between those 4 things whenever I'm trying to get the molecular shape. So sometimes that can be a little bit helpful also. All right, anybody have questions so far? It's not that bad once you get to doing it. All right, so if you didn't pull out your practice, if you will get your practice out, because we're going to look through some of those. Looking through this page. So it had the chart, and then we talked about some covalent, and so it was a practice behind that. Because once again, I don't want to look at anything ionic because that's not going to be affected by VSPER. You go through your practice, I had mentioned that on some of the things that I gave you practice for covalent, there were words about what shape it was, but you wouldn't know what those were yet. So now you can go back and apply those as you go through your practice. All right, so the first one I have is silicon with 4 hydrogens. So the first thing I got to do is make my Lewis structure. So silicon is from group 14. So it has 4 valence electrons, and then my hydrogens have 4. So I have a total of 8 valence electrons to work with. Step always for a covalent compound. Second step, put my element that needs to be in the middle. So in this case, silicon. Hydrogens would never be in the central. My third step is attach everything with just a single bond. All right. I have 4 bonds, so that is 8 electrons. So I don't have any electrons left. Had a problem on this one, or is that a good structure? Good structure, right? The only thing that needed an octet was the silicon, and it has 4 bonds. 4 times 2 would give me its 8. All right, so now we're going to move on to the structure. So the first thing that I would be interested in is the domain. So I'm interested in silicon. That is my central atom. And I have 4 things attached to it. 1, 2, 3, 4. So its domain is 4. So domain, that is the very first column that you're looking at. And that kind of narrows down the chart overall. So my next thing that I need to do is I need to make my generic formula. So I have my central atom A. I have X, and there's 4 things bonded. So that would be X with a 4, and there are no lone electron pairs. So once I figure that out, now I'm ready to come and look on my chart and match that one up. Tetrahedral, exactly. Remember, you're going to come over and read the shape here where it says molecular geometry. So if you had trouble finding that, if you look on here, our first thing we said was that there were 4 domains. So that got me to that section. And then I would have needed to go through these. It was the very first one. So then I came over and I read that shape, and that would be the molecular shape of that molecule. Any questions on that particular one? All right, let's just do another one on there. I'm just going to do the next one because it kind of shows something that we need to look at. So first thing, it is a covalent compound. So I'm going to get total electrons. So I have 4 from my carbon. Each chlorine has 7, and I have 4 of those. So that gives me 28 of 32. All right, which element am I putting in the middle? C. And so my next step is just attach all of these by just a single bond. Many, we had 32 electrons, was that right? All right, so when I did that, I had to form 4 bonds, and so that would give me 8 electrons. So that would give me 24, I believe. Can I do math? I can't really do math sometimes. Got 24 more to work with. So I need to give my terminal atoms an octet. So I'm not dealing with carbon at this time. I'm dealing with these. And halogens are always going to need 6 more. Right, so 6 times 4 is 24. So I don't have any left, but that's okay because that is a good structure, right? Everything has 4 bonds, or a bond and 3 pair, but a valence electron. So now when I start trying to look at my shape, I have a lot of lone pairs floating around, but they are not on the central atom. So I am not concerned about those. We made that statement on our little table here. The only thing I am worried about is carbon. So my first thing I'm going to find is domain. If I look at it, 1, 2, 3, 4 things attached to it. So that gets me to my section here on this table. And then carbon is my central. It has 4 things attached, and I don't have any lone pair. So it is AX4. So it actually turns out to be the same thing as the one above, right? It looked a lot more complicated when we drew it, but all of those lone pairs that are on terminal atoms do not matter as far as figuring out what the structure is. Right, why don't y'all try the next one? PCl3. So start the same way, start with your total number of valence electrons. Always where you got to start. It's group 15, and then all of the chlorines are halogens, so group 17. Everybody get the generic formula with your X's and your A's? Obviously, we have to have an X. How many A's do we have? How many things were attached to it? 3. Did we have any lone pair of electrons? Yes. Should have had 1. So we'll go through it, but that's kind of what your generic would have been. So how many electrons did I have to use? Total all your valence, 26. Yes. All right, so I'm going to put my phosphorus in the middle. Once again, halogens would not be in the middle because they really only have one place to bond. And so then I'm going to attach my 3 fluorides with just single bonds, 2, 4, 6. So now I have 20. So same thing, I'm going to work with my terminal atoms and give them a valence. So they each need 6. Right, so I had 20, that took 18. So now I have 2 left. So what are those 2 going to go on? Phosphorus, perfect. They're going to go right there and everything has a good octet. So once again, I'm going to start with my domain. It still is going to be 4. 1, 2, 3, and then this lone pair will count as 1. So my domain is 4. So I am still in the same area as our other example. But now instead of XA4, we're looking for an XA3 and then 1 electron pair. So when we find that one, what would its molecular shape be? No matter if you mispronounce it, I could be mispronouncing it. Yeah, that's it. Trigonal, trigonal, I've heard it all different ways. Pyramid. So you look for the domains, you look at how many things are bound to the central atom. And a bond counts the same as an electron pair. So like if I just had, let's say that this would be an example. I think this is CO2. Okay, so there, that carbon, and I'm always worried about the central one, it has 2 double bonds, so that would just be 2 domains. It only has 2 things attached to it. Whereas I looked at it in water, we said this had a domain of 4, right? Because I have 1 bond, 2 bonds, so that's 2 things. 1, another lone pair, so that gives me 3, and then another lone pair would give me my 4. So any kind of bond counts the same, and then a lone pair counts the same. All right, why don't y'all give the next one, NCl, a try? Nitrogen group 15. And then once again, some halogens. 3 halogens. So tomorrow on the quiz, you obviously won't have to do shapes. That won't be till the test. So you will do 2 of each type of structure.